Okay, this is the second hour of Physics 1C for March 2nd, and we're going to continue talking about Flux and Gauss's law. And now that we've effectively derived it, let's go ahead and actually put right here what at least one book defines as the definition of Gauss's law. So this is what, this is Surway and Jewett uses this definition right here. It says the net flux through any closed surface surrounding a point charge Q is given by Q over epsilon naught is independent of the shape of that surface. Okay, so we derived it for a very special case. We used a point charge, we used a spherical surface, but what we're going to try to argue now, and what Gauss's law states, is that it doesn't actually matter what the shape of the surface is. And that's ultimately what the most powerful thing about Gauss's law is. Okay? The net flux is always given by this, okay? And it's completely independent of the shape of the surface. Okay. So we want to talk about this problem right here. But before we do it, I want to describe kind of a way that we can understand Gauss's law. So I want you to think about, we're just going to kind of conceptually kind of try to come to understanding of why this might be true, okay? So if we think about what we've talked about in previous chapters, if I give you two different situations, if I say that I have a charge that I call positive Q right here, and over here in a place that's not in any way connected to that first one, so just another point in a different region of space, if I want to draw field lines for these two objects, one of the things that I told you about these field lines is that they have to be proportional to the size of the charge, right? So for example, if for this one I draw, just to keep it really simple, if I draw 4 field lines coming out of this one, like this, then what was the rule I told you last Thursday about this one? How many field lines should I draw coming out of the positive 2Q charge?
8.
8, exactly. So we should have twice as many, right? So we've got twice as many field lines, right? Okay. So now what I'm going to say is that when we've talked about the electric field in the past, one of the things I told you was that the region where the electric field lines are the most dense is the place where the electric field is the strongest. And by density, I kind of mean number of lines per unit area. So we could make the following statement. The size of the electric field is proportional to the number of field lines divided by area. Kind of like density in a way, right? The density of the field lines. The places where you have more field lines per unit area, you're going to get bigger electric field. And what I mean by that is that if I were, for example, to look at a surface, imagine that I've got a surface that kind of goes into the plane of the board, and it edgewise crosses like this, right? And let's say that's just the length and the size of my surface right here, right? So again, this is a surface. I guess I could draw it. I don't want to draw extra lines on here. Just imagine that this surface is a flat surface that is oriented kind of like this, flat, just like this. And we're looking at it edge on, right? So in this position, how many field lines are crossing through that surface? 3, right? And technically there would be more, right? Because remember that these electric field lines that I'm drawing, they're just drawn in 2 dimensions, but they're really 3-dimensional, right? There's field lines that would be coming, this way and this way and this way, and field lines going into the screen that way and that way and that way, right? So there's more, but on our picture, for what we're doing here, there's only 3, right? Okay, what happens if I move it up to here? How many field lines go through the surface now?
1.
Right, and if I moved it to here, it'd be 2, right? So if we wanted to rank which area has the strongest electric field, right? It would be, this one would be number 1, right? The strongest. This would be second strongest. And then this would be the weakest, right? Of those 3, right? The field gets weaker because the density of the field lines goes down. Yeah? Now that's one way of talking about it. You could also say, well, what's the point of doing that? Because we already know that the closer you get to the charge, the bigger the field is. That's a stupid thing to talk about, right? Well, it turns out to be the case that it's a relevant thing to talk about, because the next thing we can do is say, since we know that the electric field is proportional to the number of field lines per unit area, or the density of the field lines, right? Then what happens when we take that quantity and we multiply by area? Well, we already know that that's how you get flux, right? What were you going to say, Kim?
It becomes independent.
It becomes independent.
Just like that radial.
Right, so electric flux, which we said was defined as electric field multiplied by area, right, must then be proportional to, well, the number of field lines per unit area is the electric field. If you multiply by area, like this is our area right here, then you just get number of field lines, right? Does that make sense? So this gives us a direct proportionality between flux and number of field lines crossing the area, right? So the number of field lines that penetrate through your area it's going to tell you basically something about the flux, right?
Yeah.
Okay.
Yeah.
So let's now start putting some shapes around these objects. So we put a shape like that, like a circle, or a sphere. Imagine that it's a sphere. And put a circle over here. They're the same size surface, so those are the same, right? How is the flux through the one on the left going to compare to the flux of the one on the right? Which one's going to have more flux? And keep in mind, it's really just
on the right.
Right, and so if this had a flux over here, and it's going to be 8 lines, right? And over here, the flux is just going to be 4 lines, right? So the flux over here is twice as big, right? Can everyone see that? Twice as big, okay? So that's consistent with Gauss's law, right? Because it says the net flux, ignore this part, is given by Q over epsilon naught. So it's related to the size of the charge. So if you double the charge, you keep the surface the same, you double the flux, right? Let's call this surface 2, because I'm going to draw another surface on here as well. So suppose that I draw another surface, and I make it bigger. I don't know, like that or something like that. And I call that surface 3. What's the flux through surface 3 going to be? And again, we just want to count lines now, right?
Same.
It's the same, right? It's 8 lines. Now that's where this portion comes in. The net flux through any closed surface surrounding a point charge Q is given by Q over epsilon naught, and it's... So any, right? We covered that now. It's any closed surface that actually surrounds the charge, right? Let's see if you can... Okay, we gotta do one more thing, actually, don't we? Sorry, there's one more thing we gotta do before we can keep going. Now let's draw a different shape, okay? Because that's the part we haven't talked about, is the shape. So what happens if I put a box on here? And we'll make the box, like, purple or something. So we'll call that surface 4, right? What's the flux through surface 4 going to be?
It's equal.
It's the same, right? It's still... Again, all you have to do is count how many lines... 1, 2, 3, 4, 5, 6, 7, 8. All 8 lines actually go through the surface, right? Sorry. So that means the flux in all cases is the same. The only way to actually alter the flux... Well, there's 2 ways, I guess. One is to change the amount of charge inside, okay? The other way is to just move your surface somewhere, all right? So finally, to see if... so we've covered all the pieces of this, right? The net flux through any closed surface is given by q over epsilon naught. It does not matter what the surface is as long as it's closed. It has to be closed. And it has to actually enclose the charge, actually. But it's also independent of the shape of the surface itself, right? Doesn't matter. You get the same answer, regardless of whether you choose a small sphere, a large sphere, a box. You could also choose any type of surface you want to. Okay, it can be any shape of surface you want. All right.
How is this experimentally verified?
How is it experimentally verified? What do you mean?
Is it possible to be experimentally verified? Is there like a
Sure.
unit of
I mean,
flux
so there's
measurable?
yeah. I mean, so okay. Do we have flux meters? I think there's flux meters. Yeah. Pretty sure there are flux meters, but if you, it's more of a mathematical statement though, right? Because based on these definitions, all of this stuff has to be true, right? Like,
Yeah.
let's get into more of that later though, because that's an interesting question. I remember seeing flux meters at some point, but it may have just been magnetic flux meters, because measuring magnetic flux is, as we will find out later, probably a little easier, or at least measuring change in magnetic flux is a little easier, because we're going to see that change in magnetic flux is something that's very measurable. Would you measure flux absolutely or not? Not entirely sure, but it seems like it would be possible to do so. So let's bring that up a little bit again, a little bit later. Maybe during the break we'll kind of look into some information about that. So what about this? Suppose I have a scenario where I take a charge and I put it right here, right? And then I give you another surface, okay? And again, let's use a cube because it's easy to think about a cube. So now we've got our field lines, right? And I'm going to draw extra field lines for this one. They go like that. They go like that. They go like that, let's say. Okay. And let's say those are the only things that actually pierce through our surface, right? What's the flux through this surface going to be? Let's call it S5. And again, we're only considering this system here. Don't worry about the other ones. Although I can probably
It must be 0.
Yeah, why does that have to be 0?
Because there's no charge inside.
That's one way to think about it. The Q inside Q is 0 inside of here. And that's what
every field line that keep going.
No, go ahead. That's right. Go ahead.
Every field line that enters the surface comes out of the surface.
That's right. So this would be like saying, okay, if we count the field lines that go into the surface, right, there would be 1, 2, 3, 4, 5. They all come in at this point. So you get some, remember that flux going in was negative, right? So you get like -5. You could say like -5 in, but then every single one of those also leaves. So it's -5 out. So when you count the total number of lines, when you say a line coming in is negative and a line going out is positive, I guess I should write that down because it's not obvious. This is negative flux. And then a line going out. This gives you positive flux. Then yeah, every line that comes in, all 5 lines automatically leave it, right? And if you want to, you can try to imagine drawing some kind of a surface such that this wasn't true, but you won't be able to do it. So to relate this back to your question about can you experimentally verify this stuff, Cam? It's really more about geometry at the end of the day, right? It's the geometry of a vector field that defines how this all works out, right? The reason why you can get flux through this surface, this surface, this surface, and this surface is because the way that flux is created is by electric field lines crossing through a surface. And the only way to create electric field lines is what? What's the only way we've learned so far to create electric field lines?
We need to have like some source charge.
You need a source, right? You need a source, right? Exactly. You need a source. So it's really a mathematical expression, because Gauss, after all, was a mathematician, right? And when Gauss's law is something that is true in other scenarios too, I guess you might say. So yeah, it's more about geometry of how these vector fields work. And you can verify it very easily by just drawing really simple configurations, right? We can do complicated configurations too if we want to. But before we do that, before we go on, I just want to stop for a second and make sure. Does anyone have any questions? Okay. Let's just talk about negative charge real quick, because we didn't mention it and we should. Come on. All right. So for negative charge, it works just the same. You just get negative flux. So if I have a negative charge Q right here, and I tell you that it has 4 field lines coming in like this, remember the negative charges have field lines that go towards them, and then I enclose them with some surface, call it S6 or something like this. For this one, we'd say the flux would be equal to negative 4 lines. Or, by using Gauss's law, we can actually explicitly say that the flux through this surface is going to be negative charge divided by epsilon naught. So you get negative flux because it's flowing in. It's like a sink. Okay, let's see if you can all answer these questions now. So it says, a spherical Gaussian surface. Now here's the first time you're seeing this phrase. All of these surfaces are just described as Gaussian surfaces. Okay, it's just a surface. It's not anything special. Spherical Gaussian surface surrounds point charge Q. All right, so point charge Q. Oops. Get a sphere, put it around it. Like there, maybe. And actually make it a sphere. Okay. So we've got a spherical Gaussian surface. So this is our Gaussian surface. It says, describe what happens to the total flux through the surface if the charge is tripled. What's going to happen to the flux? So if I define the flux for this surface that has radius r to have a flux that we just call phi. Okay, that's our flux. What's going to happen to the flux if the charge is tripled?
The flux is tripled.
Yep, so phi is going to go to 3 phi. If I write it like that, does that make sense? Triple the flux, right? What happens if the radius of the sphere is doubled?
Nothing.
Nothing, right? Flux is the same. Because again, it does not matter what the shape of the surface is. What happens if the surface is changed to a cube?
Nothing.
Yep, flux is the same.
No change.
No change. And what if the charge is moved to another location inside the surface? Now, we haven't actually addressed this, but what that would mean would be we take our charge here and we move it, like let's say over here. What about now? Now let's draw the field lines.
Doesn't change.
It's not going to change. That's the right answer. Yeah. So D is flux is the same. It doesn't change. Now this one, I think it bears actually looking at what's going on, because I don't think this is obvious at all. This is where things start to get, I think, a little bit trickier. At least the first time you're learning this stuff. So now if I draw my field lines for this guy, I'll just draw 8 of them. So I certainly thought, when I was first learning this stuff, that this should change something. Because after all, the flux is kind of like more intense over here, you might say, or something, or it would seem like it is. But in reality, what's different is just that the electric field is stronger on this side, right? But that doesn't change the flux at all, because there's still 1, 2, 3, 4, 5, 6, 7, there's 8 lines that go out, right? And regardless of where I put the charge, that's not going to change. So, what we've learned is the only way you can actually alter the flux through a closed surface, and again, I have to emphasize, this only applies to closed surfaces. The moment we open these surfaces up, things completely change, okay? But as long as you're talking about a closed surface, the only way that you can alter the flux is by manipulating the charge itself. Double the charge, triple the charge, change the charge to a negative, etc. You add more charges into the system, right? And we can look at systems like that. Like, we can do something like this. Let's say that we have a system that looks like this. I put a charge here that is 5 microcoulombs. And I put another charge over here that's 2 microcoulombs. I put a charge right here. We'll put a negative charge here. This one's going to be negative 3 microcoulombs. Okay, so these are positive. And we'll do one more. We'll put one down here that's negative 4 or something. All right, so we've got these charges here. Oops, this is negative. Okay. And now I'm going to draw some surfaces, okay? So we'll draw one surface like this. We'll choose different colors for each of these. We'll draw another surface that's like this. Will that change if I... No, it won't. Whoops. Let's draw that with red. Draw another surface like this. We'll draw a surface that goes around all of these. We'll call that good. So we'll call this one S2, and we'll call this one S1. No, 3. Sorry, S3. So what, can you all tell me, what would the flux through surface 1 be? It's the blue surface here.
It shouldn't just be 1 microcoulomb.
Yep, and then we got to divide by epsilon naught, right? So we'll call it 1 microcoulomb.
Yeah.
What's the flux through surface 2 going to be? And I don't know if you noticed what he did there, but you take 5 minus 4. Those are the only... See, remember, it's only the charges that are actually inside of the surface that matter, right? In fact, usually the way that we write, what I will usually write for Gauss's law, is I'm going to write up here the charges that are enclosed by my Gaussian surface. So ENC stands for enclosed. These are the charges that are actually inside of the Gaussian surface, basically, right? So let's look at maybe somebody else answer. What do you get for surface 2?
Positive 2.
Yeah, surface 2 closes 5 minus 3, right? So plus 2. And then the last one, which was this black one, phi 3. What's that one going to be? Surface 3 has how much charge inside of it? How much charge is inside surface 3?
Positive 3.
Yeah, 4 plus 2 is 6 minus 3. That's right. 4 plus 2 is
Oh.
6. Oh, this one's negative.
That's negative, yeah.
Doesn't look negative because I didn't put a negative sign in front of it.
Be negative 5, right?
So negative 7 minus 2 is negative 5. So negative. And that's Gauss's law. Does that make sense?
Yes.
It's
Yep.
Like what Gauss's law is in and of itself is pretty simple. Applying it is going to be quite tricky, as you will see, both in your homework problems and the problems we'll do for the rest of the class. But just keep in mind that that's the important thing to understand. It's only the charge inside that's actually going to matter. If you have a charge outside your surface, it makes absolutely no difference. Now let's look at more carefully at the scenario we just talked about here. Do we want to? I don't know. I don't know if this is going to be helpful, but if I take a look at like a dipole arrangement, right? So a dipole looks like this. You've got positive here, you've got a negative here, and the field lines associated with the dipole basically do this. They go like that. You get one that kind of comes up like this, and then they kind of start to expand out a little bit. Eventually, they kind of go off to infinity. And so these go this way, this way, this way, and they kind of come in from infinity over here, and they come in from infinity like this. They go out this way, and then over here we get kind of the same picture. I really shouldn't be curling these up so much, but that's okay. 1, 2, 3, 1, 2, 3, and we'll just make this one go out like that, and we'll go in like this one here. So this is a much more complicated type of arrangement of the field lines, but all the rules of Gauss's law still apply. So for example, if I drew a surface around these objects like this, dipole is going to have the same charge. So if this is Q, this is negative Q over here, right? What would the flux through that be?
That's just 0.
Yeah, it's 0, right? Okay. And if I enclosed only one of the charges, what would I get for the flux?
It'd be plus or minus
That one charge.
1
Yeah,
Q.
so if I do like
epsilon.
this, you'll get the flux over here is just Q over epsilon naught. If I do the flux over here, it's going to be negative Q over epsilon naught, right? So as complicated as those field lines are, we still know the answer of what the total flux is through any surface that we draw. It's one of the most powerful things about Lydia. I think I need to move to another notebook because this is starting to get really laggy. So what I'm going to do, the other things we need to do are these. So I'm just going to select all of them, and we'll go to a new notebook. This one is just getting super laggy. What's up? Can someone have a question?
I thought someone did, but I kind of have something. So if we like just make our sphere bigger and bigger, or our surface bigger and bigger,
Yeah.
is there like some agreed upon, like, is there a net charge of the universe? Do people say it's like just 0, or?
That's a great question. What do you all think? What would the net charge of the universe be?
0.
Why would it be 0? Why wouldn't it be positive?
I mean, I would think because we're like sort of like a closed system, so we're not getting anything in or out.
Yeah, but what if there's just like a lone positive charge somewhere?
Where would it have come from, though?
I have no idea.
So let's think about where positive and negative charges come from. If I tell you that you can take a plastic comb, and when you comb your hair, that as a process of combing your hair, if it's really dry, let's say you take a hairdryer and you dry your hair off as much as you can, you get your comb completely dry, it's no water, no moisture on it at all, and you comb your hair, and you've got, let's say, really thick hair, and you comb your hair, I've told you before that what happens in that process is that electrons from your hair transfer over to the comb, and the comb becomes like negatively charged, basically, right? But to begin with, both of them were neutral, because most objects in the universe are neutral, right? So it's really just the transfer of electrons from one object to the other that actually changes the charges, yeah? And while a comb and your hair don't represent the entire universe, the same concept can be applied to anything in the universe, basically, right? So yeah. We believe that there is a symmetry in the universe between the total number of charges that exist. That is to say that... So we'll talk about cosmology a little bit here. Our current understanding, whether this is something you're familiar with or not, I think a lot of you have heard of the idea of the Big Bang, right? That's not something new to people, right? The Big Bang?
Yeah. No, that's not new.
But do you really understand what the Big Bang means? I don't know. I really don't know what it means to you personally. But I'll talk about what I know minimally about it. I'm not a cosmologist. But I am a particle physicist, and the two things are very tied together when it comes to the Big Bang. So the idea was that when the universe was, when it begun, after the Big Bang, that you started off with just energy, pure energy. It was so hot that really nothing could really form. You couldn't have atoms, you couldn't have electrons, you really couldn't have much of anything. It was just raw energy, right? But as the universe started to cool down, you started to have things appear, okay? Things like electrons, things like quarks, some of the fundamental particles in the universe. But what we believe happened in that time was that you would have had to satisfy charge conservation. So that is to say that if you pop an electron into existence, right? So if during the time of the Big Bang, you start off. I guess we'll do some. I don't want to confuse you too much, but imagine that this line right here represents a photon. Okay, and let's say that in the early universe, the entire universe was just nothing but energy, so nothing but photons. Okay, maybe some other particles too, but I don't want to confuse you by going into those. Let's say you have a photon like this. One of the things we've learned through a guy named Richard Feynman, who was a scientist in who worked on particle physics in the 40s and 50s and 60s, I want to say, is that this photon can basically turn into, this isn't going to look exactly right. If any of you know enough about this, you might have some issues with the way I'm drawing this, but a photon can basically spontaneously turn into what's called an electron, which we know about electrons, right? But it can also turn into a positron. So basically, that photon, which carries a charge that's equal to 0, can basically, I don't know, you want to call this creation. I don't like the word creation, but this photon can kind of create what we call an electron-positron pair. This positive E plus right here is a positron. All right. Now, you'll notice that since the charge of this is 0, and the charge of this is -1, and the charge of this is +1, exactly, like the charge of the electron is exactly positive E, or negative E. The charge of the positron is, they're not different in the slightest. They have exactly the same charge, right? Then at this little vertex right here, where the photon turned into these two particles, charge is conserved, right? So we think something like this happened in the Big Bang, to answer your question, Cam. That for every positively charged particle that was created, you also got negatively charged particles. And it's not just electrons and positrons that were created in this fashion as well. The other types of things that can be created like this are all of the quarks, and the quarks make up the rest of matter. You guys all know that atoms are made of protons, neutrons, and electrons, and probably some of you also know that the protons themselves and the neutrons are made up of what are called quarks. So you can also have an up quark that's created, a U, and what's called an anti-up quark, which we use a U bar for. And in this case, the up quark has a charge that's positive 2/3. Positive 2/3. And the anti-up quark has a charge that's negative 2/3. Both of these are times E, the electron charge, basically, right? And every bit of matter that was created in the early universe, we think followed some kind of pattern like this, basically. So that you would always have equal amounts of positive and negative charge. So we believe the whole total...
Okay.
The total universe has to have a total charge of 0. Another way to say that is
is the same charge that we're speaking of right now in this course, is that concept still used in higher physics, or is it like some other different concept?
What do you mean? No.
Like how it is with Newton's gravity and Einstein's field equations.
Okay, let's compare those two ideas. So the charges that we're talking about now, electric charges, proton charges, all those kinds of things. Your question is basically, is there a point later on in physics, when you go deeper and deeper into physics, do you start to learn a different way to describe charge? And the simplest answer is no. Now to compare that to what you're talking with general relativity, so what he's talking about is the idea that, again, I don't know if everybody knows about this stuff, so I'll just kind of throw it out there. The theory of gravity that we learned in Physics 1A is Newton's theory of gravity. And as far as we know, that theory of gravity is very, very good. It works very well to explain most known phenomenon that exist within our solar system, as well as the most phenomenon that exists across our galaxy. There are some flaws, however, and one of those flaws related to, helped Einstein to understand that it might be worthwhile to think of another theory of gravity. And his theory of gravity is called general relativity. But to answer your question, even in general relativity, we still use the concept of mass, right? It doesn't change, right?
True.
So within electricity and magnetism, the analog would be that as electric charge is to the electron, in gravity, mass is to the sun, the mass of the sun, for example, right? It doesn't change, basically, right? It's still, they're the kind of...
Okay.
Yeah, so there's no new definition of electric charge. Now, that doesn't mean that we won't come up with another theory in the future in which we realize that our ideas of electric part and of a positive and negative charge are wrong. We could just be wrong, okay? But they work really well for everything we've done up till now. They've driven the advancement of our society through the 20th century, the development of transistors, and then computers, and then smartphones, and all the other wonderful things that we have in our lives now. But it's all the same electric charges as far as we know. Yeah. The only thing that we know that's kind of weird that comes out of the new quantum mechanics stuff is the fact that quarks end up having these fractional charges. So that's a little bit weird, right? Because we thought that the electron charge was kind of the fundamental unit of charge, and it is. It's just that these quarks have fractional charges. It's just another piece of it, right? Now, I want to say something about what I described, because this isn't the whole story. I don't really need to talk about this, but I feel like I want to, so I might as well. Something I left out of this story is that in the Big Bang, if these photons quite simply just turned into electrons and positrons, right? Then on the left-hand side of my picture right here, everything that I've written is what we know as matter. And on the right-hand side is what we call antimatter, okay? It's matter that has exactly the same properties. So the positron is exactly like the electron. It has the same mass, but it has an opposite charge. It also has other very similar quantum numbers, okay? Things like isospin and other things that don't really matter for what we're talking about now. But the charge is the one thing that's different, basically, right? And we call these things antimatter. Now, what can happen is that when matter and antimatter come into contact with each other, maybe something you all know about, maybe if you've watched enough movies or Star Trek or, I don't know, Angels and Demons, talked about this as well. What happens when matter and antimatter come into contact with each other? Does anyone know?
They neutralize each other.
They neutralize each other, but you get, what do you get out of that process? Does you get anything out of it?
Light?
They produce light, yeah. You can actually run this exact picture that I have here in reverse. So an electron and a positron would come together and they would basically produce a photon, which is energy, right, or light. But much more than that, what happens when matter and antimatter collide with each other is there's basically like a 99% conversion of mass to energy, if that makes any sense. Now, why does that matter? Well, you probably know that if you go to your gasoline station, you put gasoline in your car, that your car is really not 100% efficient in converting that gasoline into energy, right? There's going to be some losses in that process. But in addition, when you just burn gasoline, you don't actually get 100% of the matter energy out of it, right? So this comes into the idea that, Einstein told us that energy and mass are related to each other through his equation, right? You take mass, you multiply by c². That tells you how much energy is contained in a particle. When you have a matter and antimatter that actually collide with each other and they annihilate, you produce, you basically, you get back almost 99% of the energy. So it's a very pure energy conversion process, matter to energy, if that makes any sense. It's the most pure version that we know of, which is why a lot of people have theorized that you could use matter and antimatter as a way to produce lots of energy for like a spaceship for long voyages and stuff like that. Because one of the hardest things about space travel is mass, right? You got to get the stuff up into space, and then you need to accelerate it, right? So if you can have the best conversion of matter to energy that you can possibly get, that's a really good thing to have. It's a better conversion than nuclear reactors, which also do a really good job, right? Yeah. Okay. So the one thing I wanted to say is this picture can't completely be right, though. Because if in the early universe, every single photon turned into some piece of matter and some piece of antimatter, we would have been left over with equal amounts of matter and antimatter, right? And then if everything was close enough together, what would probably happen? If you have equal amounts of matter and antimatter in the universe, and it's all close enough together so that it can interact with each other, what would you get?
It just turn back to energy.
Over time, it would just annihilate.
It would just annihilate and turn back to energy. The process basically continues. So every time you create a matter-antimatter pair, it's just a matter of time before eventually it finds one of its partners. Now, it doesn't have to find exactly this one. It could find another electron. Like this positron can go off and hit an electron that's coming over here, and as long as they hit each other, they're going to turn in energy, right? Okay, so that's the part that's weird. We know that we're alive, right? We know we're here, and we know we're made of matter. Right? We're made of electrons, and we're made of up quarks and down quarks and stuff like that. So where's all the antimatter? Where's all the antimatter, Where did it go? Why are we...
And that's what I was thinking with the
Right.
charges.
Mm-hmm.
Kind of like what I was thinking with the charges, too.
Yeah. So this is an unsolved problem in physics. We don't really understand why it is that, for some reason, during the Big Bang, there seems to have been there should have been an equal production of matter and antimatter. But if that's true, they should have annihilated each other, and there would be no universe, right? But there is a universe, and the universe, in case you don't know, our entire universe is made of matter. The whole thing, every galaxy, every star, every planet, every human, everything that exists in the universe, we are we have like 99.9% certainty that everything is matter, basically, right? There are no galaxies that are made of antimatter. Because if there were, they would probably collide with another galaxy at some point, and then they would just annihilate into energy, right? So everything we see is matter. So where is all the antimatter? Something must have happened in the Big Bang, in the processes that occur at that time, to kind of split up the matter. Somehow more matter was produced than antimatter, basically. Somehow. We don't know how. But
It just
I
went
will
off in the other direction.
What's up?
How about it just went off in the other direction?
It's possible that they were split so far from each other that you created like an antimatter universe and a matter universe, but then why did the matter all go in one direction? We think there's other reasons, and we have ideas. And what those ideas are, I'm not going to go into detail here. It's way beyond the scope of this course, but we do. I mean, even this stuff we're talking about is relatively beyond the scope of this course, but it's interesting. So, like, that's a big problem in physics. You could make it really philosophical if you want to. Like in philosophy, you might go into philosophy class, and one of the early questions someone might ask is like, why are we here instead of not here, right? Why is there something instead of nothing? You know, and this is a question that physicists are working on. Now, they're not working on the why of it; they're working on the how. What is the fundamental process that separates matter from antimatter? And we have some systems that we know about that behave in ways such that the matter is kind of more likely to be produced than the antimatter, which is to say that the matter might be more long-lived. It might have a longer lifetime than the antimatter, such that it just sticks around longer to where all the antimatter decays away to normal matter, and you're left with just matter, basically. So we do have some ideas. It's just we don't have a good, solid idea yet. So, anyway, to go back to your original question, we do think that the total charge of the universe should be 0, basically. But there's a lot of problems with that because, I mean, where do you define the universe, right? So it's a lot easier to just say our galaxy has a charge of 0, you know? So, anyway. I don't know about the charge of the Earth. I think the Earth might actually be negatively charged. Maybe I'm wrong about that. Maybe it's just positive. Or just, maybe it's neutral. It's probably neutral. I think the surface of the Earth has like a roughly negative charge, though, or something like that, so that the electric field in the surface tends to point downwards. But I can't remember. I have to go restudy that kind of stuff. Okay, so there's a bit of an aside. I don't know if you all found it interesting or whatever, but...
Yeah, that was really interesting.
Yeah. Okay, so what we want to do now is we want to use Gauss's law, okay, and we want to use it on a couple different type of systems. Now, where did my plane go? I didn't put it over. Well, so we're going to do a cylindrical... we're going to do a line of charge, we're going to do a plane of charge, and then we're going to look at a problem right here that's going to be kind of similar to your homework. And if we have time, we'll get to this little list right here. I don't think we will. We'll probably end up talking about this list next time. So now what we want to do is we want to actually use Gauss's law to do a calculation, okay? Is this the easiest one to do first? I feel like this is the easiest one to do first. Maybe I'm wrong. But hopefully we can all understand this. Now let's write Gauss's law up here at the top. So Gauss's law states that the total flux through a closed surface, phi e, that's net flux, ends up being equal to, this is like a triple equation, right? So you've got the definition of what flux through a closed surface is, which is to say you take a surface integral of the electric fields and you dot product it with dA, okay? You do that integral. But that's also got to be equal to the amount of charge that's enclosed within your surface divided by epsilon naught. Okay, so that's Gauss's law. And what we're going to do in the next few problems is we're going to use this to find the electric fields. So the interesting thing about Gauss's law is we don't usually use it to calculate flux, although it can be done very easily, because like obviously you just charge inside, divide it. We usually use it to find the electric field, or the charge. But what we'll be doing for the next few problems is we're going to use this equation to find the electric field. So for this one, I think what we'll do is we'll try to set it up, and then we'll take a break. So it says, find the electric field, a distance r from a line of positive charge of infinite length, and constant charge per unit length, lambda. So, infinitely long line charge. This is something that we actually talked about in the last chapter last week. we calculated, if you remember, the electric field for an infinite line charge. If you look back in your notes, you can see what the answer was. And we'll see if we can get the same answer. So we have positively charged line. We're not going to worry about the thickness of it. But it goes on forever. And the amount of charges per unit length is uniform, right? Lambda. So that means if I cut off any piece of this, I know what the charge per unit length is. So if, for example, the charge per unit length was like, let's say 5 coulombs per meter, and I cut a meter off, I'd have 5 coulombs. If I cut 2 meters off, I'd have twice as much, or 10 coulombs. So we know that the charges are basically evenly spaced throughout this object. And what we want to do is we want to find what is the electric field at a distance r away from the line. So this distance right here, if we call that r. We want to find what is the electric field at this location. What does it look like, and what is its value? All right. So for doing Gauss's law problems, there's a bit of an algorithm that you can use, and it basically goes like this. The first thing that we want to do for Gauss's law problems is, as best we can, try to draw the electric field lines. Now, this isn't always going to be possible, so I'm just going to write at the end, if you can. You might not know how to do it, so just, if you can, try to draw them. So I'm going to draw them here. Even if you didn't know anything about this positive charge, but you knew something about the way electric fields work, I think it's reasonable to guess that you could say that the electric field in this case is going to have this type of look to it. The electric field lines should be basically evenly spaced, and they should always point basically out away from the surface. Does that seem reasonable? Whoops. I'm going to copy all those. I can't control select, can I? Ah, whatever. We'll just copy, paste, 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 paste. We'll just do that. So I think that it's reasonable to assume that this is what you would guess. Does that seem reasonable? That you would guess that your electric field lines would be uniform like this? Is there anyone that would doubt that that's what they should look like?
It seems reasonable.
And can you tell me, why is this a reasonable assumption?
Is it because we know that the charge distribution is uniform across the whole line?
Sure, and why would that affect it?
Because if it wasn't uniform, then in some places the field lines would be longer than others, right?
Well, remember the field lines, they go off to infinity, right? You're thinking of the field vectors,
Yeah.
right? Yeah.
Mm-hmm.
So maybe you might say that if it wasn't uniform, like if the top had more charges than the bottom, then the field lines would have to be kind of angled away from each other, right? But if they're not, then, well, that means that, will it let me reverse this? That won't let me reverse it, will it? I want to flip horizontal, right? Yeah. I'm drawing way too many lines here, I guess, but... Copy, paste. Copy, paste. Okay, so those are kind of like what our field lines look like, right? Something like that. Delete some of these extra ones. And in addition to this, you have to take this picture that I've drawn right here, and you basically need to rotate it 180 degrees to get all the field lines, right? Because there's also going to be field lines that come directly towards me. There's going to be field lines that go directly into the page. And then there's also going to be field lines kind of coming off at an angle, such that if we looked at it from the top down, what we would see is that we'd have our positive charge, right? Well, can anyone tell me, what would the picture look like if I put my eyeball up here and I look downwards at this object? What am I going to see?
Like a plus sign of sorts.
By that you mean like the field of a oh yeah, you're saying like this, like basically like this, and this.
Yeah.
Yeah, but in addition, we could also draw more lines in here, right?
Yep.
Okay. You can always draw more or less if you want to. You can double the number in a given problem. It's fine to do that. So given that this is kind of the picture of what it looks like, now what we have to do is this. We need to use Gauss's law. We want to use it to solve for electric field, right? And in order to do that, we need to construct a surface to surround our object with, through which we will calculate the flux, right? So the second step that is usually written for these things is to choose a Gaussian surface. This is the interesting thing about these type of problems. I think it makes them very different from really anything you've seen probably in physics. Maybe you've seen problems like this in mathematics. I really don't know. But choose a Gaussian surface. Okay? Now, the goal, when you choose this Gaussian surface, is to make it such that it vastly simplifies the problem. So I'm going to add to this. Calculation. We want to choose a Gaussian surface that's going to simplify the calculation. Now, in order to do that, the only thing that we can really control, there's two things we control, I guess. We can control the strength of the electric fields and the angle that it makes with our Gaussian surface, right? Basically, we can control this dot product. Ideally, what we want to do is we want to make the dot product either just equal to EdA, which would mean the surface and the field would have the same direction, or we want to make it 0. Does that make sense?
Mm-hmm.
Now, in this case, can you think of a surface that we can surround our object in here such that the electric field lines will always be perpendicular to the surface at every point, that it'll pierce straight through the surface?
A cylinder.
Yeah, cylinder.
Or a box. I mean, if you're
Well, so
2D case.
So in the 2D case, yeah, a box would work, right? If it really was a two-dimensional situation, this would work just fine, right? Now let's see why. The box would work just fine because on the left-hand side, everything is perpendicular to the surface. On the right-hand side, everything is perpendicular to the surface. What about the top and bottom?
No flux.
No flux, right? We basically did a problem like this earlier, right? So a cube seems like it might be a really good choice. However, we need to rotate that cube so that it actually works in this situation, right? Because a cube, if I looked at it from above, would now look like this, right? And that is not going to work, right? Because you're going to have field lines that are at an angle here, field lines at an angle here, etc., etc. So if we just look at the top-down view, we know that the only way to make sure that these field lines are always perpendicular to the surface is the cross-section has to look like a circle, right? The cross-section of our Gaussian needs to look something like that. Would everyone agree? Because then that's a right angle, that's a right angle, that's a right angle. Okay, so a cube isn't exactly going to work anymore. A rectangular prism won't work. A triangular prism won't work. But what kind of object will?
A cylinder.
A cylinder. Exactly. So you just take that and you make a cylinder out of it, right? So I'm going to make my cylinder start right here. And I'm going to draw it down to here. And the interesting thing about this is we don't need to draw our cylinder such that it covers like every single field line, right? It just needs to cover some of them. So that's going to be our Gaussian surface. And I hope you understand why we chose it, but just to reiterate, the reason why we choose this is because it's going to make it so that this portion, the dot product, is either going to end up giving us the maximum value, where the field lines always point at right angles to my surface, or it's going to give me 0 on the top. And that's what's going to vastly simplify the calculation. That's the hard part. Picking the Gaussian surface is the hard part, because it could literally be any surface your imagination can come up with. Our surface could have been in the shape of a rabbit if we wanted to, but obviously a rabbit would not make these nice, like, simple things, so we choose a geometrical object, the way I would say, that exploits the symmetry of the problem. This type of problem has what we'd call cylindrical symmetry. It is a cylindrically symmetric electric field, right? I could rotate my cylinder that I've put on here in any direction I want to, and it is not in any way going to change the relationships that we described. All of the angles will maintain them exactly what they are. That's because a line with field lines emanating out from it is a cylindrically symmetric field. So we choose a cylinder to exploit that symmetry, right? Okay. I think we'll stop right there for a second, but I will say that at every point on our surface now, what we can do is we can draw a little vector to represent what I'm going to call our surface vectors, right? At every point that we don't have to do it everywhere, right? We can basically draw a dA. And dA is going to represent, well, the surface, basically, or a portion of the surface. And we see that, luckily, at every single point, we either get a right angle like this, or we get an angle of 0, like this right here. So we're going to take a break until 4:20, and then when we come back, we're going to finish this problem.